Good evening, class. Today's the day. We're going to be starting on the unit circle, starting in our math packet, unit 3, topic 1, part 1 on page 13. So I'm starting with the warm-up where it asks us to fill in the missing values for sine and cosine only. In the first column, I believe are all the cosine thetas. Remember, you don't want a naked trig function. You always want to say either sine theta or cosine theta. And in the last column, it tells you what quadrant the angle occurs in. So if we start with our first row, the information they give us is that cosine theta is 3 over 5. So that's adjacent over hypotenuse 3 over 5. That means it's a 3, 4, 5 special right triangle that we learned about. And so what I did over on the right side of the table is I drew a triangle in the first quadrant as the last column tells us to do. And since we have sides of a right triangle of 3 and a hypotenuse of 5, I filled in the last missing side, which is 4. If we use Pythagorean or our memorization of 3, 4, 5 right triangles, we know that the missing side is 4. And then when it asks for a sine ratio from the same theta, from the same angle, starting from the central angle, starting from near the origin, that ratio is going to be 4 over 5. For our next row, this time they give us negative 3 over 5, and they tell us that the triangle is in the third quadrant. So I drew my right triangle in the third quadrant, and I labeled the opposite side from theta. I labeled that y value negative 3 and the hypotenuse as 5, since sine is always y over r. And now, because the triangle has rotated to the third quadrant, the missing side is negative 4. It's on the left side of the origin on the x-axis, and that's where x is negative. So now when I go to do my cosine theta, it's going to be negative 4 over 5 because of that triangle rotating from quadrant 1 to quadrant 3. I'll do one more, and then I suggest you pause and fill out all the way through everything except the last 2 rows and see how you do. So the last one I'm going to show you is they give us a ratio of negative 5 over 13, and they tell us it's in quadrant 2. So I'm drawing my special right triangle in quadrant 2, and I believe we talked about special right triangles that are 5, 12, 13. And so when my triangle is in quadrant 2, the only side missing is 12. The 5 is negative again because it's on the negative side of the x-axis, on the left side of the origin. And then I do my new ratio. This time it's a sine ratio. So I do opposite over hypotenuse, otherwise known as y over r, and that's going to be 12 over 13. So please pause the video and try the next few rows except for the last 2. Here are the answers for everything except the last 2. Hopefully you did okay with those. Notice how on the left I named what the special right triangle is. 7, 24, 25 is not one that we discussed before, but that's another special right triangle only based on sides or Pythagorean. And then, of course, we have our 1, 2, square root of 3 right triangle, which is, of course, our 30, 60, 90 right triangle. And so depending on what quadrant it is, helps determine what the signs are for the ratios. For the last 2 rows, we are doing unusual ratios, starting with cosine 0. So we know from page 12 that cosine theta can also be rewritten as x over r. And we know also, if it's the unit circle, that if I've got cosine 0, our radius is going to be 1. So if my radius is 1 and my x value is 0, and it tells me in the last column that the angle is between 0 and pi over 2, which is 90 degrees inclusive, then I know that this ratio has to be a quadrantal. The quadrantals, if you remember, are when basically when we're not able to draw a right triangle at all. It's either going to be aligned with the x-axis or y-axis. In this case, it's aligned with the y-axis because that angle or that ratio, 0 over 1, is going to be a ratio based on the coordinate 0, 1. Remember that our coordinates are x is cosine when the radius is 1, and y is sine when the radius is 1. So our point has to be 0, 1, in which case, if I'm now doing a sine ratio, if our y value is 1 and our radius is 1, then the ratio for sine can only be 1. Now, for our last one, they give us this time sine theta is equal to 0, and that's going to be y over r. So y is 0 and r is 1. It's our unit circle. This time it tells me that our angle is going to be between 90 and 270. So this time it's going to be the quadrantal on the x-axis, -1, 0, because I know, and this is something that you should memorize, that anytime I have sine or cosine that are values of 0 or 1, those are quadrantals, meaning it is a point that appears on either the x or the y axis. In this case, it's going to be on the x axis. It's going to be over to the left of the origin. That makes the point -1, 0, actually where our angle is 180 degrees, in which case, if it's cosine, it's x over r. The x value is -1, the r value is 1, and so the cosine theta is -1. On our next page, we're starting to study our circular functions or our unit circle. And the thing to remember with our unit circle is that the radius is always 1. And as we started to discuss on Wednesday and Thursday, we started talking about the triangle inside the circle. So when they talk about the relationship between the trigonometry of the right triangle and the unit circle, they are talking about rotating our special right triangles around our unit circle. And remember that mostly when we're using that unit circle, we are going to be doing everything in radians. We've got to get used to angle measurements using pi. So we've done this before. We've got our point x, y on our unit circle, and it looks like this. And I just want to move this down a little bit so that you can see that I'm still doing the same ratios that I did when we did this a few pages ago, when we first put our XY point on our unit circle. And so with that point, we need to remember from Algebra 2 that when we did our Ferris wheel, we always talked about sine ratios. Sine ratios, sine ratios, sine ratios to measure how high up on the Ferris wheel we were. And if you remember, our sine ratios were measurements of y. If we're measuring how high we are, that is an up-down movement. That's a vertical movement. And so that vertical movement is sine. That measures a y distance. Concurrently, when I go left and right, that's an x distance. That x distance is cosine. So every point on our unit circle can be thought of as every x is cosine t, or it can be cosine theta, and every y value is sine theta. The reason that works is because our radius is 1. So if sine of the angle is y over r, then y over 1 is always going to be y. So sine is always y. Cosine of the angle is going to be x over r. R is 1 again. So x over 1 is x. If I do cosecant, which is the reciprocal of sine, it's not going to be y over 1, but 1 over y as long as y isn't 0. Same with secant as the reciprocal of cosine, 1 over x. And then we have tan, which is a measurement of y over x. It's opposite over adjacent. And then down below, when we talk about tangent, we have a new ratio called the tangent identity. If tangent is y over x or opposite over adjacent, and I know that every y value is sine of the angle and every x value is cosine of the angle, then y over x is the same thing as sine of the angle over cosine of the angle. So I've got another definition of tan using our unit circle. The only thing I didn't talk about was cotangent, and of course that's the reciprocal of tan. So rather than y over x, it's going to be x over y. On this page here, I have a copy of the unit circle. And what I did was, in yellow, is I basically highlighted one special right triangle that I could start rotating around the unit circle. Generally speaking, there are only 2 types of triangles that we rotate around a unit circle. One is our 30, 60, 90 right triangle. The other is our 45, 45, 90 right triangle. I highlighted the triangle that starts with this theta here of pi over 6. So I went over here and I drew the triangle more clearly to show that pi over 6 is 30 degrees. And if it's a right triangle, we've got our 90-degree angle and, of course, our 60-degree angle. And we know from the previous page that anytime I have an x value, that's going to be cosine, and our y value is going to be sine. So if I start making ratios from my special right triangle, sine is always opposite over hypotenuse, or x over y. That's going to be 1/2. Or you can start memorizing all of these coordinates that go around the unit circle. It's the same values over and over again. And the reason that is because you're rotating the same triangles around this unit circle. So the same ratios are going to appear over and over again. And the only thing that's going to change is the signs. If I reflect over the y-axis, then the x value changes. If I reflect over the x-axis, the y sign changes. So same values, same coordinates, same x's and y's, same cosine and sines, all over the unit circle with different signs depending on what quadrant it's in. Now, what I would do is I would hit pause here and I would start filling out my own unit circle. Since I have to start using mostly radians, I need to not only label this unit circle with all of the degrees, I need to also label it with our radians so that we have a good idea of where we are in the unit circle, what quadrant we're in, what ratio we're doing, and what is the measurement of the angle we're using that bumps up against the origin and starts rotating from the positive side of the x-axis. So hit pause, and you can also see here where it says positive and negative. I started labeling what we learned on Thursday, which is all students take calculus, which talks about what angles or what ratios are positive and negative in each of the quadrants. And so you might also want to include that in your unit circle here when you're labeling all your XY points and all of your angles, both in radians and degrees. So please hit pause, fill in your unit circle, compare it to page 16. Now we're going to use that unit circle to start getting used to what the measurements of cosine and sine are. We're not going to worry about tangent yet. We're not going to worry about cosecant or cotangent or secant yet. We're going to mostly focus on cosine and sine. And so once again, I took the triangle that's in the first quadrant and I rewrote it here so that you can see if I am starting with an angle, that's pi over 6. Okay, so I'm saying that the angle up against the origin here is pi over 6. If I start rotating that right triangle around the unit circle, the only thing that's going to change is the signs on each of our coordinates. For example, here is the point in the first quadrant. It's right here. And that point, when I have a measurement against the origin, that central angle of pi over 6, which is the same as 30 degrees, I'm going to have an x value, which is the same as cosine, of square root of 3 over 2, and I'm going to have a sine ratio, or y value, of 1/2. When I rotate that triangle, or better yet, I reflect that triangle over the y-axis, the only thing that changes when I reflect that triangle is the sign of our x value. And that makes sense. If I reflect a point that's 3, 3 in quadrant 1, and I reflect it over to quadrant 2, that point, if it's a true reflection, is only going to be negative 3, 3. So the same thing happens with my coordinates here of square root of 3 over 2 and 1/2 reflected over the y-axis means it's now the negative value, negative square root of 3 over 2. And then, of course, I'm the same height as I was, just as I would have been on the Ferris wheel. So my sine value stays the same. It stays positive. If I reflect over the x-axis from the first quadrant, the x value stays positive. Cosine stays positive. But our y value, since it's now below the x-axis, that's negative. So depending on where our special right triangle is reflected to, that will determine what our sine and cosine is. So looking at our unit circle with only the 4 triangles, I'm going to start with the middle calculations, and basically I am just reading the values off of my circle. So if I'm cosine of pi over 6, I am here in the first quadrant. If I am in the first quadrant, then cosine of pi over 6 is the x value of that coordinate right here, this little pink point. And that tells me the cosine or x value is square root of 3 over 2, and it's positive. If I do the y value of that same point in quadrant 1, it's going to be sine, and sine of pi over 6 is going to be 1/2. Again, I'm just pulling the values off of the circle. Some of you may be like me and later on use this triangle moved around the unit circle to come up with your ratios. But for now, we're just getting used to the fact that we understand symmetry, and symmetry changes signs, and therefore we're going to just read off of the unit circle to come up with our different measurements. 5 pi over 6 is in quadrant 2. And so if it's in quadrant 2, cosine, which is a x value, is going to be negative. So now, rather than positive square root of 3 over 2, like in quadrant 1, it's now negative square root of 3 over 2. And our sine value remains positive because I'm still above the x-axis. 7 pi over 6 is going to be in the third quadrant. If it's in the third quadrant, both x and y are negative. Cosine is x, negative square root of 3 over 2. Sine is the y value at the same point in quadrant 3. If I just read it off of the xy coordinate there, sine is y, so that's going to be negative 1/2. Last one is in quadrant 4. In quadrant 4, x is positive, y is negative, x is cosine, and cosine is x, square root of 3 over 2, x is positive, y is negative, sine is y, negative 1/2. And then I'm going to show you what happens if I go around not counterclockwise to produce positive angles, but if I go around the opposite way, if I go clockwise, I still go around to the 4 quadrants. My triangle still reflects between those quadrants. But now I'm going to basically read these angles from a different perspective. Where I used to have pi over 6, I'm now going to have negative pi over 6 because I have rotated clockwise almost back to the initial position. And so I've got a reference angle of pi over 6. If I've got a reference angle of pi over 6, that's the same thing as negative 11 pi over 6. Therefore, cosine is x. It's going to have the same x value as cosine pi over 6. And the same thing is going to happen here. Since I'm matching up positive and negative angles in the same quadrants, all of my ratios are going to match. The same thing is going to happen if I go around the circle more than once. If I go around the circle more than once, remember what we talked about, coterminal angles. So these last two columns are saying pi over 6 is the same as 13 pi over 6 because I've added 2 pi. Pi over 6 plus 12 pi over 6, 12 pi over 6 is 2 pi, is 13 pi over 6. So again, my, my cosine ratio is going to be the same as cosine of pi over 6. And my sine ratio is going to be the same as sine pi over 6. And so I'm making connections between reflections, which are symmetry, and periodicity. Periodicity means how many times am I actually going to circle around my unit circle? That's going to determine what my ratio is. Now we're going to do the same thing with a different triangle this time. This time, rather than the angle in the first quadrant being pi over 6, this time it's going to be pi over 3. So you're to think of your special right triangle that's reflecting, you're to think of it as being a 60-degree angle here next to the origin. In which case, our 1 and our square root of 3 change places, and notice what that does to our coordinates. The 1/2 and the square root of 3 over 2, they change places. Because now I'm not doing it from the perspective of 30 degrees or pi over 6. I'm doing it from the perspective of 60 degrees or pi over 3. So once again, with the table below, you're just to read from the different points depending on what quadrant you're in and how many rotations you've done. So if I go up, it's up here. If I go up here, I'm going to fill in all of my sine and cosine ratios based on where I'm located. Anytime it asks for sine, I'm going to look where pi over 3 is. That's in quadrant 1. Sine is y. I'm going to look and see what the y value is for sine in that first coordinate. And I'm going to write square root of 3 over 2. The last one, as you can imagine, is the other special right triangle that we talked about. The other special right triangle is our 45, 45, 90 right triangle, in which case I'm no longer dealing with 1/2 and square root of 3 over 2. I'm doing square root of 2 over square root of 2 because that's based on our rationalized ratios. I can't have that square root of 2 as our radius. We always want the square root to be in the numerator. So all of these have been rationalized for you already. Your angle is always going to be some kind of measurement that's based on 45 degrees. Pi over 4 is 45 degrees. And so since we have pi over 4, all of our measurements are going to be based on that. So now when I want the highlighter to work, it doesn't work. So as I expose these, if I'm working from the first quadrant has a coordinate of xy of square root of 2, comma, square root of 2 over 2, in which case when I do cosine, which is the x value, it's the same as the y value. And then the only thing that's changing again is depending on what quadrant you're in, will depend on the sign of the x and the y values. So you should practice using this basically abbreviated unit circle and filling in your sine and cosine ratios to practice using the unit circle. I think that was our last slide for today. Yep. We're going to do page 21 on Monday in preparation for Tuesday's quiz. So I hope you have a good weekend, and I'll see you on Monday.